So today I will speak about one of the core topic of my work, that is the role of geometrical confinement that I will define in the next slide. And in particular, I will discuss with you if it is possible to make it a control parameter. And I will also discuss with you what is the main question of this talk. And I hope that at the end, I can come up with a at least partially positive answer. So what do I mean with the confinement? So we know about many physical system or soft matter system. Here, for example, you have an example of water molecules or even liquid crystals or any other kind of system. And typically these systems are studied in the bulk pretty much because the bulk is a friendly system. Typically in the bulk you have translational invariants, and then you can have all this kind of Fourier approach, and you can really exploit the fact that the medium is at least on some length scale homogeneous. However, in many situations, these systems are not unbound. Rather, they are bounded. Actually, in every real experiment, these stuff, they are bounded. They live inside some vessel. So this is more or less, if you want the picture. You have your system, your bulk system, about which you know quite much. You know quite much about its bulk properties. You can know typical distance among molecules, energies, or even transport coefficients, heat conduction, diffusion, viscosity. And then the question is how all these properties are affected when you confine the system. With confinement, what do I mean? Well, I mean that I have a system and somehow I put in a box. This box is made of another material. Typically, this material is considered as a simple one. It acts, if you want, in mathematics, you would say, as a boundary condition. So you don't look at the physics of the container, you just look at the physics of what is inside. But the fact that you have this boundary, then it affects the property of the system. For example, in quantum mechanics, you know that silica are different on the surface, but this also happens for classical systems. And why we should bother at all about this confinement? Okay, fair enough, it's there. But one can also say, who cares? Well, the problem is downscaling. So when you go to big machines or big apparatus or apparati to smaller one, as the process of nanotechnology requires, what's happening is that you're changing the surface to volume ratio. So when surface to volume is very small, indeed, the system is controlled by its bulk properties. However, when you go down, what's happening is that surface to volume rises, pretty much because surface scale as the second power of the size of your system, whereas the volume as a cube. And therefore, what's happening at the surface becomes more and more important. So in practice, what's happening is that not only this is perturbing the system, this if you want is the negative side of the story, you can also tell in a positive way that by controlling the surface of this container, you may aim at controlling what's inside. Okay, so in practice, instead of changing the molecular properties of your system in order to induce, for example, a phase transition at a given temperature, you keep the system as it is, but you confine it. Or by confining, you can prevent a phase transition like water. Nano-confined water doesn't freeze at -2, -3, -10, -15 Celsius, pretty much because of the confinement, because of the interaction with these walls that confines it. So it's also a chance of controlling. On the one hand, it happens in the process of miniaturization. On the other hand, is a chance to control. So where these happen? So does this feature happen in nature naturally? Well, one of the most famous cases is micro and nanofluidics. This is the king of these cases. Here is really a field where people, by properly tuning the shape of the channel, and by properly tuning the forces inside this channel, they get some different features. For example, they can induce droplets, or they can merge droplets, or they can make every kind of control chemistry inside there. In other cases, this blue energy, so where people try to extract energy by mixing fresh water and salt water, and typically putting a membrane in between. And again, you force these ions to go through this porous membrane, and by doing so, you may extract electric energy or electric current. And this also happens in nature. These are ion channels in all our cells. Muscle contraction and all this kind of stuff is controlled by ion channels, or aquaporins, in which you control the motion of non-charged substances. Aquaporins, you control the transport of water molecules that are uncharged. But then the confinement can also use to control, and this is already something that people are already doing. It's not science fiction. And one of the most interesting fields is this continuous flow chemistry, in which people really use these micro and nanofluidic devices, and they make chemical reactions inside there, really at the microliter scale. And then the idea is that in this scenario, everything is much more controllable. And then instead of scaling it up at the industrial level, you simply multiply it up. So you have many of these microchannels, one next to another one, and then you can really make a plant out of it. You can really produce kilograms and tons of chemicals out of it, but without the process of scaling up. So without the problem of recalculating all the rates when you have a big tank. And again, here the idea is that by controlling the shape of all these conduits, you may control the chemical reaction and what kind of chemical reactions. Another case is typically sensors. Sensors typically are very small, and again, surface to volume rises up. And this is another case in which you use the shape of these objects to control it. And the last one that I find very interesting is this soft and nano robotics. They typically rely on these hydrogels. But again, every time you deform a hydrogel, in practice, you are moving quite a volume of electrolytes, so water with ion suspended in, and again, controlling, knowing their dynamics in different scenarios may be important to know the performance of these soft robotics. So these are the scenarios that we have, and then how we can do it. So how we can really synthesize, and what are the typical length scales. So there are different techniques. We have standard lithography, by which you can produce channels with features of around 1,000 micron. Then you can do two-photon lithography, and then you go down to 100 nanometers. So you can have objects with features around 100 nanometers. And then you can go really down up to nanometer via carbon nanotubes or nanopores. And there you can really have pores of the size of some nanometer. On the other hand, you can also think of take them from nature, from biological world. And then you have aquaporins and ion channels, whose size typically is a nanometer. Then if you go up with length, you have axons, the axons of our neurons, and cytoplasmic strands that are small pipes depicted here inside plant cells. This is around 100 nanometer. And then eventually you can do it in the computer. This is the supercomputer of Barcelona. It's very nice because it was in a former church. And you can do it numerically. So you can put in the computer and then you can do it. So these are the kind of ways in which you can study or have confined systems. Now, question, is confinement a control parameter? So let's first be clear. What do we mean with control parameter? Control parameter, for example, let's take temperature. We know that we have a soft matter system. By tuning temperature, so by controlling temperature, so taking temperature as a control parameter, we can change, for example, we can induce a phase transition, for example, or we can change the transfer coefficient of a given system, or if you prefer, pressure or chemical potential or other parameters. So a control parameter is something that you can tune easily, and by tuning this parameter, you can vary the performance or the feature of a given system. Now, in this regard, confinement is not really yet a control parameter, for the very reason that it's not so easy to tune it. Let's say if you take confinement from nature, like ion channels, well, ion channels are proteins and they are as they are. You cannot simply say, oh no, you know what, I would like to change this small atom here instead of the other one. It's not so simple, even though it's not impossible, but it's not super simple. And the same is for these carbon nanotubes. You can synthesize them, you can study them, but you cannot really change the shape at your wish, or at least not now, not yet. And the same problem you have on the numerical side. Indeed, you can do numerical simulations, fair enough, but the problem is that every time you change the shape, you have to make a brand new simulation. So now the problem is that it's not yet easy to change it, and this is one of the reasons why people have not used it yet to fully control the dynamics of the system, even though there have been several attempts. So today, I will show you an alternative approach that, as the picture is showing, is more based on Blackboard tools that allows to capture some of the main feature of the confinement in an easy way, such that you can really tune this parameter in an easy way. And in this way, you can indeed look if there are some new regime, something that is really qualitative different because of the shape of the confinement, or if in practice, if you want, is everything the same, you simply change a bit the numbers, okay? That's the big question I want to ask. Is there something new? Is there really some qualitative different regime that you can come up with by tuning the geometry of the confinement, or in practice is always like if it were bulk, but you simply change a bit the numbers? So in order to do so, I take a study system, if you want, it's like the Ising model or the hydrogen model for this problem. And I study systems that are confined in a corrugated channel. All the calculation and the example I'll show to you are typically 2D. So you have translational invariance in the direction perpendicular to your screen, but the same technique can be applied for axial symmetry or even non-axial symmetry. Let's say the less symmetry you have, the more integrals you have to calculate numerically. The more simpler system, the more you can proceed analytically. But the technique holds for all these cases. And this drawing is already showing, if you want, 75% of the masses. So you see you have the walls, this green stuff, and then the white area in between is where the system can be. For me, the system in this case are these green beads. And this is already showing to you that there are different length scales. You have the size of the system, in this case, the diameter of the bead. Then you have the transverse length that can be wide, like here, or can be narrow, like here. And then you also a longitudinal length. If instead of this varying shape, you would have a flat channel, then this would be just a matter of the transverse length, one transverse length versus the size. And no longitudinal length, because it would be translational invariant along this axis. Whereas the fact that the shape here is changing, so the fact that indeed we are playing around with the geometry, with the geometrical confinement, is introducing a longitudinal length scale, so you are not translational invariant anymore, and this transverse length scale is changing, is inhomogeneous. There are places where you can accommodate plenty of particles, other places where maybe a few can fit. Okay, so the idea is that to have simple system embedded in such a scenario, and then we see how does their dynamic changes upon changing the shape. And so the idea is to come up with some analytical model such that the shape can be changed at wish, and then you can have as many results as you want with a standard laptop in a matter of tens of seconds. Okay, so how do we do so? Now, here I'm going to show you how to do so. So this is the only slide of equation that is really important, so please pay attention just to this one. After this slide, all the other one with equation, you can forget equation. But here, equations are really bringing the physics. So let's say we have a simple system, a set of non-interacting particles, and then we describe the dynamics of their density. This P, X, Y, T is their density, the probability of finding one particle at a given location at a given time. And as usual, this is a continuity equation. On the right-hand side, you have minus the divergence of the flux, and this is linear response. So this flux is proportional to the forces that are applied. And here comes the approximation and therefore the physics. So first of all, instead of having weird boundary condition on the all these boundary condition on the channel walls, I simply said I have a potential W, and this potential is done in this way. It diverges if the particle tries to leave the channel, if the particle tries to enter in the wall, whereas if the particle is within the wall, you can have any kind of soft interaction, electrostatics or van der Waals, magnetic, whatever. And then here comes the approximation. So we say that our probability distribution indeed factorizes. And we say that we have an unknown function as a function of x and t. And concerning the transverse direction, so y is the transverse direction, x is the longitudinal direction. Concerning the transverse direction, we assume that we have the Boltzmann weight. You see, e to the minus beta w, where w is the potential, this is the Boltzmann weight. So this means equilibrium, and already means that there's no flux along this direction. And in particular, we decide to normalize this by this factor, e to the minus beta f, called like that. And this is nothing but the integral of it. Okay, this is simply this integral. So what happens? That this f, indeed, if I simply take the log, is minus kt logarithm, and this is the local partition function. You see, it's the integral of the Boltzmann weight along the transverse direction. So this is the local partition function, and the log of the local partition function is the local free energy. So this is where the physics is. This is telling us that, okay, I can do this procedure, and this F indeed is my local free energy. So it's not a random function, it's the local free energy. Now, the interesting point comes here, and this is the last step. I can take this equation and integrate along the transverse direction, because I'm not interested in the transverse direction. I'm interested in transport in the longitudinal direction. If I do so with this ansatz, I end up with this equation for my rho xt, that is the probability of finding my particle at a given position x, notwithstanding the transverse one. And this again is a continuity equation, fair enough. And here you see, it's like before. Instead that now this potential has been replaced by the local free energy. So this is telling me that whatever shape I have, whatever potential I do have, I plug it in here, I do this ansatz, and this ansatz, it can be shown very rigorously that this is the first term of a systematic expansion, and the expansion works provided the channel is changing very smoothly. It's a kind of long wavelength expansion. So it's a gentle channel, it's not abrupt. So provided you have such a geometry, then you have this equation. Now, the beauty of this equation is the following, that if you look at steady state, as in many cases people are, steady state, so rho is not changing in time anymore, then you have the derivative of something equal to 0, and this is super easy. This means that this quantity inside here must be a constant. And this is a first order differential equation whose solution is on Wikipedia. And this you can integrate easily with the computer, and it can be integrated very, very quickly. So in practice, now we have a tool that allows us to characterize the dynamics of confined system, changing the shape of the confinement and the interaction with the wall at wish. So now let's see if it works and what we can get out of it. So let's look at the problem of electrolyte flow through a pore. So here now I've changed a bit the color. So we have the walls now are yellow. The area inside white is where particle can be. And this red region here is the debile. Let's imagine that you have some fluid. There's some salt dissolved in the fluid, and the salts may dissociate. You can have some charge on the wall of your channel, and then you have the onset of the double layer. Clearly, we look at the simple case where the Poisson-Boltzmann equation is linearized, and we have the bilocal. Therefore, we have a debile. Okay, and we can apply different forces. We can look what happens if you apply a pressure drop, an electrostatic potential drop, or a chemical potential drop, as it happens in this blue energy device. And how do we proceed? Pretty much as I showed before. We integrate along the transverse direction, and we apply this long wavelength expansion on all the equations that we have to cope with. Now, to be more specific, which equation we look at? Well, we have, sorry for this, I'm running out of battery. We have Poisson-Boltzmann equation that is controlling the charge distribution and the onset of the electrostatic potential. And we have then the equation for the ion density that, again, is assumed to be overdamped, as I showed before. So velocity relaxes very, very quickly. And we look at steady state. Steady state simply means that the average of the flux is equal to 0. And then we have also for the fluid. Fluid, again, these are micropore. So we have low Reynolds. So we have Stokes flow. And we assume our fluid to be incompressible, like water. And clearly, the system comes with boundary conditions, because boundary conditions are encoding in practice, the interaction, the physics between the confined system and the confining wall. And this boundary condition can be as you wish. For example, you can have conducting wall, so you fix the electrostatic potential. You can have the electric wall, therefore you fix the electrostatic field. And again, for the fluid, you can have impenetrability, so the fluid cannot leak through the channel, and you can have no slip, or you can also decide to have a slip condition. All these can be encoded within the same technique. And you do this lubrication approximation that is nothing but this long wavelength expansion that I mentioned before. So now I skip the algebra because it can be a bit boring. And then let's come to what do we get. One stuff that you can measure is the relation between fluxes and forces. For example, we can look at, and this is called Zagger matrix. And for example, we can look on the left-hand side, fluxes are electric current, JQ. We have a flow of solution, Q, and JC prime is the flow of solute on the top of the flow of solvent. If you choose these fluxes, and as forces, we choose the electrostatic potential drop, the chemical potential drop of the salt, and the pressure drop, then the Zagger matrix is symmetric. And then we can look at the different transport coefficient, these curly L's. And in particular, there's a funny scenario for this curly L12 that is equal to L21, because for this choice of variables, the metric is symmetric. That is, you see the electric current that I have if I do apply a chemical, a drop of the chemical potential of the salt, or is the excess flow of salt that I have if I apply a delta V. Look at the figure here. This is showing for you this value, this matrix element, as a function of delta S, that is nothing but the logarithm of the maximum amplitude of the channel that you have here, divided by the minimum amplitude. So it's a way to capture the geometry. If the channel is flat, delta S is 0, because H max is equal to H min, and log of 1 is 0. And then if the bottleneck goes to 0, then delta S goes to infinity. But typical values of delta S are in between 0 and 3 here, and plotting up to 5. So here what I'm showing to you is that this transport coefficient, the funny point that this transport coefficient is growing with delta S. And this for me was funny, because typically you imagine that if you want to transport something, that the current is maximized when the channel section is constant. Whereas this is showing that for these off-diagonal terms, you appreciate that these L12 and L21 are off-diagonal. For these terms, you can amplify the transport by making the channel more corrugated. Okay, so first of all, not only you can control, but you can also start having some a bit counterintuitive effects. Now, let's move on and let's see what happens if I apply a delta V. Now I have a fluid, I have my electrolyte, apply a delta V, and therefore I have forces acting on the ions in suspension, and these ions will set in motion, and these will set in motion the fluid. This is the electromotive flow. Now, typically the electromotive flow look like this. It's like a plug flow, where this decay of the velocity field occurs on the debye length, and then once you are a few debye length away from the wall, charge is in practice 0. It's not exactly 0, but it's in practice 0. Therefore, force is 0, and then the velocity profile is kind of flat. Now, the problem is that here, due to the varying section of the channel, you have this profile in every section, but then you have to enforce that the volumetric fluid flow, so the integral of this flux must be homogeneous, right? Because otherwise, if at the bottleneck you're transporting 1 liter per second, and at the center of the channel you're transporting 10 liters per second, then where are these 9 liters per second going, right? So this value must be homogeneous along the channel, because the fluid is incompressible. Otherwise, its density will pile up. So what the system can do is to set up local pressure gradients to compensate for this flow that will be different in the wide section of the pipe and in the small section of the pipe. And then you have in practice that everywhere you have to sum up this propagating plug flow, this is called plug flow, and this back propagating Poiseuille flow, whose shape is a parabola. Now, if you sum up these two functions, you can have different kind of functions. And here I'm plotting them for you. So here, this kind of parabola is the flow that you have at the bottleneck. All the fluid is going the same direction. At the bottleneck, you have the debye length is comparable to the side of the channel, and that's why you don't see this very plug flow, rather a kind of parabola. Then, while you move towards the center of the channel, you have that the velocity profile becomes more flattened, and then it even bends down, and eventually it bends down so much that at the center is even going backward. So in practice, what's happening is that this parabola here at the center is so strong that can indeed kill this flux, and then you have this kind of cartoon. So the fluid is going, so to say, rightwards, as it should, because of the delta V, close to the walls, but at the center, it is going backward. So, and then in practice, you're generating some vortexes that in the low Reynolds typically are called eddies. And these eddies are quite important because they can really, for example, enhance quite much the mixing that you have inside this channel. So, for example, if you have a chemical reaction, it can be good to have from time to time this kind of device to enhance the mixing of your chemical reactions, such that you keep all the reactant at contact each other. Now, you can ask yourself, but this stuff, does it happen always? Well, indeed, it's not really as such. Clearly, if the channel is flat, this doesn't happen. And this panel C is showing for you the velocity at this very point where you have this blue arrow as a function of the geometry. Remember, this delta S is the log of the widest over the bottleneck. And this is showing that if delta S is too small, indeed, the velocity here at the center will be positive, so towards the right. Whereas if you make it corrugated enough, you can get it. So you have to fine tune. But that's not the only parameter relevant. Also, the bile length is very important. So here I'm showing for you now 3 different values for the delta S. And here is showing you K H naught, where K is 1 over the bile length. So this is the ratio of H naught, average section of the channel, and the bile length. And this graph is telling you that even though you have the right delta S, if the bile length is too short or too long, then the velocity at this very point is positive. Namely, you don't have this eddy. But if you fine tune the bile length and the geometry, you can get it. So you see that the word fine tune appeared already quite a few times. Indeed, these kind of scenarios are attainable if you properly fine tune the parameters. It's not a set of zero measure, as a mathematician would say, but you need to fine tune a bit the parameters. And indeed, this fine tuning was possible precisely thanks to this analytical approach that allow us to really explore the parameter phase and to find and looking for this kind of scenarios. But then, okay, fair enough. You can say, but who trusts these kind of analytical correlations? And then we did indeed molecular dynamic simulations. And the simulation were guided by this model. Indeed, in the simulation, we had to go in the nonlinear regime where fluxes were nonlinear with the force because of signal to noise. But indeed, we found this local backflow, even though it's not symmetric. But you see here, arrows are going to the right, and then they come back, and here they go to the left. And the overall flow, in this case, is to the left, okay? So somehow it worked, and it worked pretty much for those values of parameters that you would expect from the model. So the model is predictive, and it can be checked against very detailed molecular dynamic simulations. But that's not the end. Typically, when you have data, then you look at the data. And first of all, these numerical simulations show that you have a concentration polarization, and this phenomenon was known. And this you can see also here. Here you have orange, you have much, many salt, and red, you have less salt. And here the graph is quantifying it for you. So this is the position along the channel. As in A stands for angstrom, so these are real units. And this you can see that here you have a region where you depopulate of salt, and here there's a region where salt is overexpressed. And this was something known, concentration polarization. But something was not known, was local electron neutrality breakdown. What is happening is that here I'm plotting in this blue cyan scale the local charge. And while the blue, a part of the noise, is showing to you that the local charge in the fluid phase matches the charge in the solid phase, clearly with a minus, such that in every slice of the channel, the charge in the fluid compensates for the charge in the solid. If you go high enough with the corrugation, you see that indeed you don't get that anymore. So there's a region clearly here where the local charge in the fluid is more than the charge on the on the solid, and then clearly this is minus that quantity is compensated elsewhere. So in practice, you have the onset of a dipole. So in practice, you have the onset of an antenna. So this is telling you that if you have a flat channel, you make it corrugated. Not only you change the transport, but you can also change the electrostatic field that you perceive outside of it. So, so this I found very interesting. And also this local electroneutrality breakdown was something that in many, many models was given as granted. Many, many models were based assuming local electroneutrality. Whereas this doesn't have to be like that. There's no thermodynamic constraint that enforces local electroneutrality. Clearly, you have global electroneutrality. And indeed, you can break local electroneutrality by playing with the shape and by looking at these resonances. Okay, fair enough. Then let's give a bit of a twist, because you can say, okay, fair enough.
Paolo,
please.
Paolo, I think you're running a bit over time.
Oh, then I quickly converge. Let's say you can do the same also for other systems. In particular, you can do it for rods. But then I will go very quickly. Let me just say that you can do the same technique. And in this case, we could check against experimental data. And indeed, this graph is showing to you this. So the dots are data from experiments, and the lines are the prediction of our model. And indeed, there are some regimes in which the model doesn't work very well, but there are some other regimes in which the model is working a bit better. And fair enough, we can use it to design channels to separate rods, but this I may tell you later more in the question session. And then this is a bit of a resume of what I showed to you, that you can use this geometry to tune the performance of this confined system. And let me just come to the final slide. So I hope I have convinced you that confinement can be used as a control parameter. So you can use the geometry to control what's happening inside. And I leave you with the last slide that is simply an outlook of all the possible systems that this stuff has been applied to, or it is en route to being applied to. And with this, I thank you very much for your attention. And I'm sorry for running out of time.
Thank you very much, Paolo. That was very interesting. Maybe we have time for one quick question.
Maybe I can ask a question. Can I?
Yes, go ahead.
So the shape of the channel that you engineered, how did you came up with? Did you optimize over the parameters in some way, or it's just a trial and?
Good point. No, at the moment, I just look at cosinus, and I was mainly adjusting the parameters of the confined system, but also vice versa can be done. You can fix the property of the confined system and adjust the shape. Clearly, in my equation, everything comes through dimensionless numbers. So clearly, I always have a kind of resonance in transverse length scales. Okay, so if you have something that is 1 nanometer and you put in a channel that is varying on the micrometer scale, they barely see each other. So these already appear from the model, but you can apply any shape you wish, and you can optimize. You can use it to find the best shape for a given task.
Okay, thank you.